Alright, let's start introducing our new operation. Let's start thinking of what we can do with our scalars and vectors, in particular with the scalar and vector fields. And the very first we'll consider is called the gradient. So let's take a scalar field, and as you have seen, the scalar field is effectively a function of space. To every point in this space it assigns a value. And the definition of the gradient applied to the scalar field is as follows. You take a partial derivative of that function with respect to x multiplied by the principal direction in this axis, and then you take with respect to y another direction, and so on. And what you'll get is a vector, and moreover it's a vector field because it will have different values at different points and different directions at different points. So that's the very first property I want you to remember, is that the scalar field can be turned into a vector field if you apply a gradient to it. So the I, A, J, just the unit vectors in the three principal directions x, y, z. An important note here is that there are multiple ways you can denote this operation, and a very common notation is to use this inverted triangle. And this inverted triangle is called nabla or del. So we often say gradient, but we write this operator, del or nabla. So that's actually a very useful symbol, and we'll see why it is written this way later. But for now, just consider this an equivalent ways to denote a gradient. Either just write a gradient of f, or you just write this inverted triangle. And because the result will be a vector field, this is called a vector operator. But again, you don't need to worry about this too much at this point. We'll come to that later. Then we will consider different operators. So all I want you to take away from this video about the gradient is that the gradient is a vector field applied to the scalar field, and you can denote it this way. That's it. Let's talk a bit more about the definition. What is useful about it is that we can talk not in general, we take a scalar field and we get a vector field, we can talk about point-wise. So I don't care about this gradient everywhere, I want to know it in a specific point. And to do that, you need to first get a general form of the gradient, and then you just substitute instead of x, y, and z a specific value, and then you will find a gradient at that point. And if it is two-dimensional, if your if your scalar field depends only on two variables, if you have a scalar field of 2 dimensions, you will have a gradient and associated vector field also living in these 2 dimensions. Let's look at the example. Let's calculate the gradient of a given scalar field. We'll use the definition. So by definition, the gradient of f is a set of partial derivatives and associated unit directions. So what we do is we just calculate these partial derivatives. So we take df over dx, which is 2x plus y. Then we take df over dy, which is x plus 6y z, 2z cubed. And then we take df over dz, which is 6y z squared. And then we will combine these to give us the gradient as 2x plus y times the first unit vector, x plus 2z cubed times the second, and then the third component will be 6y z squared times the last component. Okay, so that's the result of this operation. So we got the scalar field, and we got, as a result of it, the vector field with the three components, which will depend on x, y, and z, right? So it will be different at different points. Now we'll look at another version closely associated with the gradient called the directional derivative. So if we have a unit vector, which is a vector with the magnitude of 1, then we can define a directional derivative according to that rule. So we take this unit vector and we multiply it by the gradient in a scalar product way. And this is just a generalization of what we used to in one dimension. So if we have the df dx, and it is a rate of change in the direction of y in the x direction. Why is it the case? Because if we multiply that unit vector, which is 1, 0, 0, times the gradient, which is generally described that way, we'll end up only with the first component, all the rest are disappearing. So that is exactly the rate of change in the direction of y, and that's just the standard notation for the partial derivative of df dx. An important point here is that if we are asked to compute a directional derivative of f in the direction of a, and a is not a unit vector, it's not a unit vector, then you have to use a more general formula of that kind. So you have to multiply scalar product by this vector and then divide by the magnitude of this vector. So the result will be the same as if you multiply by the unit vector. So that's the most general definition of the directional derivative. Let's look at the example. Somebody gave us a scalar field and asked us to compute a directional derivative of that field along that direction at a point P with the components 1, 2, 1, minus 3. So let's again use the definition, and the first bit of definition is the gradient. So let's compute the gradient. So the gradient of f, again by definition, is the partial derivatives of phi, capital Phi is a Greek letter, with respect to x plus respect to y, and then with respect to z. So d phi by dz. If we do it according to our given scalar field, we will see that it is just 4x plus 6y plus 2z. This is written as in a sum notation, or we can write it as the component notation 4x 6y 2z. And also we note here that the A is not a unit vector, so we have to get the magnitude. So the A here is the I, which is effectively 1 times I, plus 0 times j, because there is no second component, and minus 2 times k, and we can write it as 1, 0, minus 2, and the magnitude of that vector will be 1 plus minus 2 squared, taking square root, is square root of 5. So that will give us a unit vector A divided by that magnitude will be 1 over square root of 5 times that vector. So there's two facts we got. So we know what is the gradient, and we know what is the effectively unit direction, what we want to use for the directional derivative. And with that, we can just write down the definition that unit vector times the gradient, as we just seen a minute ago, and that will result in something which will still depend on x, y, and z. So what we do now is we use the value of the coordinates of the points which we're asked to compute this derivative at, and put it inside x, y, and z. So that's effectively saying that x equals to that, y equals to that, and z equals to that. And if we'll substitute that inside the explicitly dependent on x, y, z components, we will find the directional derivative, and if we simplify it, we will get that, and one step further, we'll get 4 times square root of 5, or approximately 9. And that is the answer to that question, so either of that will do. But you need to not just write the answer, you need to explain where it's coming from.